Hi guys, and welcome to this WACE Academy online lesson on dynamic equilibrium. This lesson will cover Unit 3 Chemical Equilibrium Systems, points 5 to 7. Today we'll go over how to describe a system that is in dynamic equilibrium. Then we'll cover how and why some chemical reactions are reversible. Finally, we'll look at how changing the temperature of a system can affect its dynamic equilibrium, and how we represent this with a diagram. So let's refresh ourselves on what dynamic equilibrium actually is. When we say a system is in equilibrium, we mean that the concentrations of the products and reactants are always staying the same. Dynamic equilibrium is a special kind of equilibrium. The concentration of products and reactants stay the same, but they are also reacting all the time. This means that the forward and backward reactions are going at the same time, so there's no net difference. We can see a classic example of this is if we put some iodine crystals in a beaker and heat it up. The beaker has to be sealed off so it's a closed system, because we cannot form an equilibrium in an open system. Heat energy can enter the beaker as we heat it, which causes some of the iodine crystals to vaporize. Eventually, the amount of vapor and the amount of crystals will remain constant, but the forward and back reactions are still happening constantly. The reasons we can't see a change is that the crystals are turning to gas at the same rate the gas is turning back to crystals. So now that we can see that some reactions are reversible, and that when we put a reversible reaction in a closed system, it will eventually form a dynamic equilibrium. We usually use examples where the reactions are highly reversible. However, when a reaction is only a little bit reversible, it can still form a dynamic equilibrium. But what makes some reactions more reversible than others? In really reversible reactions, the forward and backward activation energies are similar. That means that if the system is receiving enough energy for the reaction to go forward, it can easily go backward too. However, in some reactions, the activation energy for one direction is much higher than the other. That means it will be much harder, but not impossible, for the reaction to go in that other direction. An analogy you could use is a bunch of people being told to run across a field, but one side of the field is much lower than the other. It would take a lot more energy to get to the higher side than it would to get back down to the lower side. Therefore, we can sort of assume there would be a lot more people hanging around at the lower side of the field because they don't want to spend the energy to get up to the high side. However, if the field was level, then there would be pretty much equal numbers at each end. Alright, so now let's talk about how temperature can affect dynamic equilibrium. You'd assume that the more heat you apply to a system, the faster reactions will go. So in that case, the forward and backward reactions will still be going at similar speeds to each other, but just a lot faster. But in dynamic equilibrium, applying heat, or taking it away, can actually change the ratio of products to reactants. It can make one reaction faster and the other slower. But isn't that weird? Why does it favour one reaction and not the other? Let's take a look at why this actually happens. So we know the reactions can either be endothermic, which absorbs heat, or exothermic, gives off heat. We can demonstrate this with a diagram. Let's consider a basic reaction, A plus B forms C and D. We'll say that the forward reaction, going from AB to C and D, is exothermic, meaning it gives off heat. We can draw a diagram of the reaction like this. This part here represents the energy that the reaction gives off as heat. It would make sense then that to perform the backwards reaction, you would need to apply extra heat, because you're doing the reverse of the forward reaction, which is giving off heat. So when heat is applied to an endothermic reaction, it will go faster. When heat is applied to an exothermic reaction, it will slow down. This is what's called Le Chatelier's principle, which says that when you change something about a system, it will respond to counteract that change. So, when heat is applied to a dynamic equilibrium, the endothermic reaction rate will increase and the exothermic one will decrease, because in this way it's using up the heat and decreasing it. So this all means that the proportion of products from the endothermic reaction is greater than it was before. Alright, that's it for today's lesson on dynamic equilibrium. Today we covered that dynamic equilibrium occurs in a closed system where the forward and backward reaction rates are the same. Some reactions are more reversible than others because the activation energy of the forward and backward reactions is similar. And finally, temperature can affect a dynamic equilibrium by changing the proportions of products to reactants. This is because the forward and backward reactions will have different enthalpies and will be affected by heat differently. Alright, so that covers it all, guys. In the next lesson, we'll discuss Le Chatelier's principle in more detail. I hope you enjoyed it, and I'll see you next time.